That's a good question. You think immediately that this is not something that is anything different from linearity, but it really is different. And let's see what it does. So let's take a look at it. Well, what do we have to do? Same change of variables, right? So y is x divided by a, but now something happens. So all right. So what happens here? This is then f of y e to the minus 2 pi I omega, and let's see, x is a times y. Okay? d what? d1. And I've got an extra a sitting out front, don't I? Because dx is turned into an a dy. Let me put my a out front here. Okay.
You also have some e going around.
So what?
Because of your substitution in top.
Oh, right. Sorry. Parentheses in the wrong spot. Here they are. My x turned into my ay.
Okay.
Okay. No, but fair point. The trick here for this one is to write the parentheses the way that I wrote them initially. Sort of foreshadowing by accident. And this is just the Fourier transform, but now instead of evaluating it at omega, I'm evaluating it at a omega. So it's not quite linearity, because I've scaled it. Basically, if I shrink time, I expand frequency. If I expand frequency, I shrink time. Right. So what this law says is this says shrink time is the same thing as expanding frequency. Or if I shrink frequency, I expand time. This sort of makes sense, because this time is sort of like telling you about periods. And periods and frequency are inversely related. So this omega axis is what we call the frequency axis, and it's sort of inversely related to the time axis, just in the way periods and frequencies are inverse of one another. Okay, so that's another useful property. So that's property 4. Now, let's see here. Property 5. So these are all sort of algebraic properties. To a calculus type property, which really explains the power of using Fourier series to do anything interesting in the world. And it comes about from integration by parts. And essentially the idea is, what is the derivative of f with respect to x Fourier transformed? Okay. So if I take function Fourier transform its derivative. Let's see here. Well, I don't know anything about the derivative, except that it is a derivative. Probably exists some places, well enough that I can write this down anyway. So what I really want to do is write this out so that it looks like a Fourier transform of f. And so the only way I really know how to do that is integration by parts, as I said. So u is equal to dv is equal to du is equal to what am I doing here? Yeah. And over here this should be df dx dx. So this is f. I'm taking derivative of this thing, and this is minus 2 pi I omega dx. E to the stuff. Okay, so then doing the integration by parts game, what do I get?
dv was, I'm sorry, I can't quite see. dv is just,
Okay, right. So the integration by parts game says I need to do what? Well, I need to do this thing here. I need to evaluate f of x and e to the minus 2 pi I omega x, evaluate between, put in a minus, so we've got another minus 2 pi I omega. My integral is in x, the omega is a constant. Now this thing up front, we sort of have to dispense with that somehow. But how? Well, probably the best way to dispense with that is assuming that this f decays, this thing's going to be 0. So if assuming we have f that decays to 0, then this is going to work out to be just 2 pi I omega f of omega. So what this does is this takes derivatives and it turns derivatives into just multiplication by a function.
Well, what if it doesn't decay to 0?
Then you must deal with these boundary conditions, which
Also decay faster than...
So it, what if f is just bounded?
if f is just bounded, well then this thing here, this is of magnitude 1. So this is of magnitude 1, so you can't really say so much about that. So you really do need some kind of decay in order to make use of this particular law. And this is actually why we
Yeah.
Right, so when you use this in practice, and of course the reason for writing this law down is because it makes solving differential equations very easy. Because you can write down some awful differential equations, got all these derivatives, don't know what to do with it, just Fourier transform everything in sight, and suddenly it's algebraic. Same stuff we had for doing Fourier series. But now we have it on an infinite domain.
Is that where the whole like normal way of dealing with differential equations like source comes from?
Yes. Or, well, historically no, but in sort of intellectual fact, yes. Right. So the benefit of this is that we've got some way to manage derivatives. Now, did we lose anything by Fourier transforming? Well, no, we've got this inverse Fourier transform. So let's verify that we didn't lose anything in terms of structure. And here's something. This Fourier transform, say, if we're working with a function in L2, functions in L2 have an L2 norm. The Fourier transform is L2 isometry. Why? Well, for one thing, because it has this inverse formulation. An inverse. So it's bijective, it's linear, so it's a linear isomorphism. Isometry means, though, that it preserves the distance, preserves the norm. So in particular, here's the formula. There's the formula. The L2 norm of these functions is preserved by Fourier transform. This is not so hard to compute, in fact. So proving this is pretty quick. So if I write this side out, so,
Wait, isn't it the square root? Or is it-
yeah, it's square root both sides, doesn't matter.
Oh, right, yeah.
Yeah, it doesn't matter. So let's see, f of x times f of x conjugate. That's this side rewritten. But I know what f of x is in terms of its Fourier transform, or rather its inverse Fourier transform. So let me write it down as such. So I'm using the inverse Fourier transform. Okay, right. So, well, what do? I bring in this conjugate. One of them's going to end up over here, the other one's going to end up over here, giving me minus. And this is a d omega. Now I have too many omegas floating around because I'm going to want to combine these integrals. So maybe call this one here I don't know how to call it something about being inflammatory, and I don't want to leave it blank.
Okay.
Zeta.
Mike C's and zetas are really hard to tell apart. And that would not result in anything much for the Z. Okay.
I'm trying to see where each part came, where each piece on this came from.
On this guy,
The whole thing on the right-hand side.
whole thing on the right hand side. So what I did is square brackets, that's equal to F, because that is F written out in using the inverse Fourier transform form.
Oh, okay, I thought we were going from.
Now, I'm trying to show this.
Okay,
Now, of course, if I start with this, then I'm done.
yeah.
So I'm gonna try to show that.
Oh,
All right, so let me rearrange these integrals a bit. Let me pull out. Let me pull out the omegas, the omega integral. So pull that one out. Push in the x integral all the way, and push the z integral to be the next level in. So this is the omega integral. This is the z integral. This is the z integral, and then this is the x integral. Okay, so I've gone all the way into out. Okay, now the benefit of doing it this way is that the x integral, when I put in parentheses there, that's equal to something kind of special. What's that equal to? Well, okay, yeah, you're simplifying it algebraically, sure, I can do that too. I can simplify this one too, so this is, okay. Yes, this is a spectral representation for the delta function. So this thing in here, this is delta of what? This is delta of, this is delta of omega z is the one we want. Delta of omega z. I'm going to integrate across z. Integrating across z. So that's going to say this thing here is going to pick up the value when z is equal to omega. End of proof. This equality, this isometry equality, has got a name. This is called Plancherel. It's the analog of Bessel's inequality in the cases of, or Bessel's equality in the case of, it's that we ran across this Plancherel equality when we were dealing with Fourier series as well. But we really worked over it then more with the Bessel's inequality where there was a greater than sign here, because you could potentially lose some energy if you didn't work with enough terms in your Fourier series. Okay, so this is really very handy. This says that if you do anything, it sort of sets up a correspondence from x variables and omega variables. You can work a hard problem here, be given a hard differential equation here. You can Fourier transform it to an easy, or potentially hard, in any event, an algebraic problem. But it's an isometry, so we have not changed the problem, really. You solve it to be something, and then you Fourier transform back to the answer x. So this is really the right strategy for solving differential equations, or at least linear differential equations.
Yeah, this is the I've seen Laplace transforms
Using Laplace transforms.
in differential equations.
Well, Laplace transforms
Do the same thing.
come from a different spectral representation for a different operator. The story is exactly the same, and we'll get there. But the story is exactly the same. That's sort of the last unit in this course, is Laplace transforms and Z transforms and such. And they all come from this same kind of machine. So the point of the matter is you can solve this hard problem, this hard differential equation, by solving an algebraic problem, which is at the very least tractable. So it turns differential equations into linear algebra and back again without losing any information. So that's the benefit of manipulating Fourier series, or Fourier transforms, rather. Okay,
What's the point of that? Is that you didn't need the inverse transform?
the point is that the inverse transform is basically the same formula as the forward transform.
Yeah.
Right. So there is this duality. Right. So this is already very good. If you can already do this, you should be very happy. But there's something even better. That this is duality. And this last property.
Oh, I'm confusing that with what you just.
What?
I'm confusing that with what you just did. I thought that's what
Right.
you just showed.
No, I did not show duality. I showed isometry. Now the last one is duality. And this one here is perhaps the most subtle of the properties in that it basically means everything that you do in the x variables can also be done in the omega variables. When you learn something about the x variables, you learn something about the omega variables. So if f of x and, I'm going to write it this way, capital F of omega are Fourier transform pairs, then it's true the other way around. So then, and perhaps, then big F of x and F of omega are also. And there's examples of these in your homework, actually, of different things that perhaps one of these arrangements is easier than the other, or in any event, they're basically the same thing. So here's something that works out pretty neat. Now I'm going to step out of L2 land to show this example. To show you that Fourier transforms, thus far we've been working with L2 Fourier transforms. They're in L2 isometry, but they actually work elsewhere. So here's an example. We've got a Fourier transform. We can take Fourier transforms of lots of things. Why not take the Fourier transform of the delta function? It's totally not at all, in any way, shape, or form. Let's even take. It's not at all, in any way, shape, or form a function in L2. It's not even a function. It is a distribution. So this formula that I've written is only valid as notation. Suppose we do it anyway. Suppose we don't care. What is it? Well, e to the minus 2 pi I omega y. Oh, really? Well, what does that mean? So this means that the delta of this guy here, the Fourier transform of this, is this function. Well, what this means is that if I take this guy over here, e to the minus 2 pi y, and I Fourier transform it, what do you think I get? This should be delta y. Possibly up to a minus sign. Perhaps my duality statement's got a minus sign that's missing somewhere. I don't think it does. Anyway, this means that basically the Fourier transform of this thing is in fact delta. And you can check this. Let's check it. You look at this,
Same thing that.
and it's the same thing we had before, and it is in fact, this is the spectral representation. So we're in great shape with this duality. This is an example of duality. But we're in great shape because the moment you compute a Fourier transform of something, then you've already got for free another Fourier transform. You already know what it is. So this makes computing inverse Fourier transforms very easy. This duality does not hold, for instance, in Laplace transforms. Laplace transforms do not have this duality. So, in fact, computing Laplace transforms is usually quite easy. Computing inverse Laplace transforms can be quite tricky. But for Fourier transforms, it's very symmetric. Okay, now, there's one final property that I want to show. And this final property is actually a property that's nicely acoustic as well, and leads us into the demo versions. So I'm going to write this final property. We'll prove it next time. Convolution. Again, this is not a property that the Laplace transform has something. It has something like this. So what it says is it says that suppose I have two functions. Oops, two functions. This is a new function. This is h of y. This is h of y. If I ask, what is the Fourier transform of h? What is the Fourier transform of h? Well, it turns out, fabulously, that the Fourier transform of this is the product of the Fourier transforms of f and g. So if this, then this. How do you prove it? It's not so hard. There's a little bit of manipulation. As I said, we're running a little bit short on time, so we'll do this next time. So it's actually not very difficult. It's just a calculation, just like all the other properties that I did with. It's just a calculation. Okay, next time. But what does this buy you? Well, remember, by duality, this tells you the same thing is true the other way around. If, in fact, I wrote this with x variables, if instead I have f of x times g of x, so I take two functions, I multiply them, then their Fourier transforms get convolved. Is then perhaps so. This is over. Now, why is this important? Well, if you look at the convolution, what does that do? See how many colors we got going on here. You take a convolution of two delta functions. Look for something good here. Good. All right. The convolution of those two functions. What's the convolution of those two functions look like? What's the convolution of those two functions look like? Well, what I do is I take F and I slide G along it until I bump it. So I'm holding F of X, and I'm going to integrate against F times G, F times G, F times G as I move this guy until at just one spot it lights up, and the rest are over there. Now, at what spot does it light up? What does Y have to equal for F and G to land on top of one another? Well, Y has to be such that the difference between these two guys here matches up. So that has to be Y in order for you to get anything. So in particular, what you end up with is it ends up F. And this is a way to write the convolution. So these are. So what this means is if you're multiplying functions, you're convolving their frequency structure. This allows you to manipulate things in a really cool way. So now let's do some demonstration aspects of this. All right, so the first order of business is to turn off silent on the phone. The second order of business is to fire this thing back up. Is the display on?
Yes.
Excellent. All right, so, and the third thing is to rotate the camera so that you can see the screen. You know you can see what. So grab that. In fact, you can just rotate the camera.
Yeah. Oh, well.
Where are you gonna stand?
Well, here's what I'm going to do. I'm going to actually, first of all, take care of some sound. So I'll do that. I have pre-prepared some sounds. I have convolved them. Okay. So the first sound. Okay, let me show you what you got on the screen here. What we have on the screen is we have, this is the omega axis, and this vertical bit is the value of the Fourier transform. This is the omega axis, this is the x-axis, and the color is the value of the Fourier transform. So the Fourier transform has certain content to it, say some sound content at a particular frequency, you will see brighter things in that. So you can see my voice as I'm talking away here. But if I then whistle, it is very localized at a particular frequency. And if I, say, increase the frequency, you can see it. And in fact, you can see some mode jumps as the resonant cavity inside my lips changes. Now, what I'm working on here, though, is typing in a fairly long command to generate some of these sounds very carefully. So that's a very particular sound, and if you read it off, it's 1,000 hertz. Here's a 500 hertz signal. And there it is, it's a little weaker. Notice that it actually, you can see there's a harmonic that's due to errors in the speakers and additional vibrations. Now let me show you the convolution of that. Yes. Volume. And what happened? Where is this marker? At 1500, which is the sum of those two frequencies. Essentially, if you take a look at it, this convolution here, the way that I drew it, I guess it went the other way. Maybe I got a minus sign in here. So what it's doing is I've multiplied those two signals. So yeah, it's a chord, but what it did is it deflected that sound signal up by modulating the frequency. Now, here is something a little more amusing. This is that sound, but modulated with a chirp. You can see that there are actually several aspects, and some that are kind of hard to see. Why are we getting several of them? Because, in fact, I'm dealing with not just e to the I omega x, but a sine or a cosine. Sines and cosines are sums of them in two different locations.